So we're the NASA XHab PETG and carbon nanotubes group. I'm David Rollins.
I'm Brian McDonald.
Zach Griffin.
Tom Lupke. Well, we're all MEs. So yeah.
All right, so we know it's more effective and less time consuming to 3D print parts than it is to traditionally manufacture them. And traditional manufacturing isn't always available at remote locations such as the space station, surface of the moon and Mars, and also remote locations on Earth. However, when it comes to the additive manufacturing, the standard thermoplastics don't have the strength that the metals of the components would have. So that's where our group comes in. We're hoping to add carbon nanotubes to a PETG plastic to increase the tensile strength of it. We are interested in how all the mechanical properties will change and also the thermal properties, but our primary goal will be to try and increase the tensile strength of that plastic.
So, like Zach said, the main objective of our project is to create a composite material using PETG plastic and added carbon nanotubes in order to maximize the tensile strength of the composite material. Along with that, a different aspect of our project is we are also just testing plain PETG plastic over 10 generations of 100% recycling. We would be extruding out new plastic, printing test pieces, and then recycling it back into plastic pellets in order to test the mechanical properties. And kind of the reason for this part would be to kind of look at the space applications of the plastic itself. Just say that NASA wants to bring this plastic to the International Space Station. They would be able to bring it up as, say, a food container, and once the food is all gone, they would be able to recycle that plastic into whatever custom part they need.
All right. So our overarching project goals. First, we're working on mixed printing and testing the nanotube composite. And then we're also working on the 10 cycles of recycling with just the PETG itself. With that second goal, we'd like to submit a research paper on the PETG recycling so it could be used by others such as NASA or whoever else might be interested in the viability of 100% PETG recycling. For stretch goals, if we have time, hopefully, we'd like to mess around more with the carbon nanotube composite. Currently, we plan on only doing maybe 3 iterations of mixing concoctions. A stretch goal would be to start to add some other additives to the material to make the things bond better together, but that's a stretch goal. Out of scope is recycling the nanotube composite. We are only focused on recycling the pure PETG. And then another out of scope is printing large functional prints with the nanotube composites, just because of how much that can change material properties with warping and stuff like that.
And then since PETG plays such a large part in our project, give a little background on the material itself. So PETG is traditionally just a very chemically inert material. Some of the bigger uses for it are it's very durable and flexible material. It's very available. It's used a lot in food containers because the FDA really likes it, just because of how chemically inert it is. It can also be used in synthetic clothing. Some of the cons to it, however, are if you use it for 3D printing, the print bed adhesion isn't very good, so you might need to use some kind of adhesive to get it to stick to the bed. Other than that, it's not necessarily your go-to material if you need a part that needs high strength material properties.
Okay, and carbon nanotubes are effectively a cylinder of covalently bonded carbon atoms. They come in 2 types. There's single walled, which you can see here, which is the single wall of the carbon atoms, and multi-walled, where it's actually a carbon nanotube within a carbon nanotube in a coaxial arrangement. And we'll be working with the multi-walled carbon nanotubes. There are a couple of nanometers in diameter and tens of nanometers in length. not to confuse them with the carbon fiber, which is actually 1,000 times larger than that, and is measured with microns of diameter and tens of microns in length. Some of the mechanical properties of the nanotubes that we're interested in is they have incredible tensile strength and elastic modulus. They're one of the strongest and stiffest materials ever discovered. The tensile strength of carbon nanotubes is on the order of tens of gigapascals. And then for the thermal properties, due to the lattice arrangement of carbon nanotubes, they are an excellent thermal conductor and actually have a thermal conductance over 5 times that of copper. So we're hoping to put these two material properties kind of into our PETG material.
So this is our block diagram of the project. The 3 main elements of the project are the carbon nanotube and PETG composite material, the 10 generations of recycling PETG, and then also fixing some of the, I shouldn't say problems, but inconveniences in our 3D printed lab. And so currently what we've been working on is some of the lab issues, including we made our own version of a pelletizer that will help us shred long strands of plastic into small bits where they're able to be recycled faster. And then along with that, we have started with the generation 2 of our recycling process.
All right, so just a little reintroduction for those of you guys who forgot statics or are in 230 right now. So the main mechanical properties that we're testing for and want to achieve is modulus elasticity. Modulus elasticity is the slope of the stress strain curve in elastic deformation of a part. So it measures how much a part can deform under stress and then still go back to the original shape. The other really interesting property we're going to look at with the nanotube specifically is a thermal conductivity. And thermal conductivity, again, is just ability for a material to dissipate heat or transfer heat through it. Example, steel has a very high conductivity, where something like rubber has very low conductivity. So we did some theoretical calculations to figure out what we might see out of mechanical properties from our nanotube composite. So the main thing we used was the Halpin-Tsai equations. These are popular equations for figuring out the moduluses of a matrix and fiber composite material. They're accurate for low volume fraction of the fibrous material, which we are planning on using. We're planning on only using between 0.1 to 5% carbon nanotubes in the PETG. As you can see, those are the equations down there. They're used to calculate the longitudinal transverse modulus. And then those in turn are then used to calculate the actual elastic and shear modulus of the part with randomly orientated fibers, which is a little different. So here's just a quick graph of those calculations. So you can see down here, this is PETG and this is ABS plastic, their ultimate strengths. As we add more composites, you can see that ideally it will get up to somewhere around the range of 1018 steel. Again, we might not achieve this 100%. It might go up and then dive down. There's no way to know, but it would be cool if it went all the way up there. Oh shoot, wrong button.
All right, so then we come to the extruding of how do we actually get our materials so we can 3D print it. This is the extruder we're currently working with. Material goes in the hopper to the auger screw. We actually have a cooling coil here to prevent heat from coming back to where the pellets are, because we don't want them to melt in the before reaching the auger and get stuck. Then, as we have mentioned for our optimal settings so far, is we have the rear heat at 185, the front heater at 195, and finally the nozzle at 225 C. And we actually have the melting point at just the extruder because we don't want it melting back in the barrel and potentially clogging it. And also we don't want the flow rate too high. Otherwise, when it escapes from the nozzle, it will actually create voiding within the material that's extruded. And then the speed of the auger is at 22 RPM. And one of the issues is we do have a new extruder coming in to help us that should be a little more robust. But these optimized settings we anticipate will not directly translate to that new extruder. So we will have to use these as a starting point and then optimize from there. This video. So here's a video of how the process works so far. Controller going. You can see the material in the hopper goes through, is extruded out of there, goes across cooling fans to a diameter measurement, and finally onto a spooler that winds it onto a spool for us so that after we make the material, we can just pull the spool right off of this, put it on a 3D printer, and start printing our parts.
And then, as Ryan mentioned, we're also working on a pelletizer. So there were a couple things that we wanted from this. We wanted it to be fairly low cost. We wanted it to go pretty quick, and we wanted it to be fairly easy to use. We were kind of looking at 3 options for that. There was using the current option that was in the lab, buying like a professionally made one, or then making our own that was based off a design that we found online. As you can see here, the one that we ended up deciding to go with was the one where we make our own based off the design. See here, there's a video showing actually pelletizing the filaments. We ended up calculating it shreds filament at about 1 meter per second.
Then yeah, the picture on the right, you can see the final product comes in as string and leaves as little pieces.
So printing with PETG is very common that it's a little bit touchy to work with as it's going through a printer. There's a very select range of print temperatures that the filament will actually go through smoothly and print evenly. So currently we're printing with a Creality Ender 3 printer, and we found that the extruder temp at 240 degrees C with the bed temp at 70 degrees C and the print speed of 40 millimeters per second helps with the smooth flow of plastic through the printer along with bed adhesion. We do rub a glue stick onto the print bed before the print to help with that bed adhesion. And then that's when that 70 degrees C comes into play. It just helps the material stick better and refrain from warping against the prints.
And you can kind of see here, this is our Gantt chart. This is stuff that we have currently all done so far. And then after the next slide, this is stuff that we're going to be planning to do in the future. So kind of big things here is that we just want to get more done, and that's going to be kind of our plan for December and early January. And you can see here, this is our budget. We ended up coming out to be just under $3,400. Most of that is just due to us needing to get the new extruder, but then there's also just a couple other small funds in there, like contingency funds, as well as needing to actually purchase the materials themselves, such as pen pellets. Any questions?
Is the carbon nanotubes just randomly orientated in there, or is there a way to find them off to get the maximum?
Yeah, so that's a good question. We assumed in our calculations that they were going to be randomly orientated. We don't have a way of mixing them anyway besides that, but when they come out of the 3D printer extrusion nozzle, we do expect them to be slightly orientated in the direction that the printer extrudes. And yeah, so that's a good point. If you want your material to be stronger in one direction, you can print so the fibers are orientated in that direction. Yeah.
So you're recycling the PETG. I know you stated that your main focus is the recyclability of just the PETG,
Yeah.
not the carbon nanotubes. When you like combine those to make that carbon nanotube PETG, like there's still gonna be carbon nanotubes in the filament, right, material.
Yeah, no, they're two separate materials. So we're mixing the nanotubes with virgin PETG material and then keeping the other recycled PETG material separate. So yeah, they're separate, yeah.
They go from the recycled components back to the. So what happens is when we have the long strands of filament, it tends to not always be the correct diameter to run through the printer. So a standard printer takes 1.75 millimeter diameter filament. So when we extrude out our material and it's not within a range of about 1.7 to 1.8 millimeters, then we just shred it back into these pellets, which are then taken into the hopper and remelted and then extruded in the next generation.
Why did you stop at 2% mix?
We went all the way to 10. I only showed 2% because previous studies that we found show that those equations start to become inaccurate around like 5% for sure. So I wanted to be conservative in my guesses. So we only showed to 2%.
Also, the cost of the carbon nanotubes is a big concern there as well. If you get up to like 10% versus the printed material.
That makes you by mass.
That was by mass. Yes, we will be doing mixing by mass. No, that was volume. Yeah, the equations are all by volume. We'll be mixing by mass, so we have it converted to mass. Yeah. Question. Any other questions?
All right, good job.
Thank you.